In this unit, we're going to look in more detail with what is going on in the atom with the electron. So we've already studied the parts of an atom. So protons and neutrons are in the nucleus. They make up the mass of the nucleus, and we know that the electrons are outside the nucleus. But what exactly are those electrons doing, and how are they behaving, and where exactly are they? So let's go back in time to the 1900s. So in 1900, Max Planck, he looked at quanta energy packets to explain hot glowing matter, and we're going to talk about him a little bit later on. And of course, Einstein's famous E equals mc squared looked at how energy and matter, that relationship. And we've already talked about Ernest Rutherford, his gold foil experiment, and he learned that the nucleus is positively charged and that the atom is mostly empty space. And now let's come to a Danish physicist who studied and came up with an idea of what the atom might have looked like. And this is Niels Bohr. So Niels Bohr, he looked at light and he was able to uh, look at that light and its association with the electron in the atom. And he came up with a planetary model of the atom. So your nucleus is in the center with your protons and neutrons, and the electrons are going around the nucleus in a definite orbit. And Niels Bohr said that every electron has a orbit that it's assigned to, and these are energy levels or shells, and you will only find those electrons in a certain energy level or shell. So Niels Bohr planetary model, here is a picture of it. So you can see that the nucleus, it's a little large, that big red circle there. It should be a lot smaller, but anyway, there it is. And then you can see that we have electrons in energy levels or shells in definite circular paths around the nucleus. Now, this is not exactly how we see the atom today, but it is the Bohr model has its uses. If you notice that the very first energy level, there are two electrons that can be found there. The second energy level, if you notice, there can be 8. And on this particular atom, we just have 2 in the third shell, but that is incomplete. And this, if you look at your periodic table, this goes along with your periodic table. On the very first row or energy level or shell, we can have up to 2 electrons. On the second energy level or shell, um, according to Niels Bohr, his orbit, you can have 8 electrons. And you can see that second period on the periodic table, you do see that there are 8 electrons because there's 8 elements and each has an additional electron more than its neighbor. So the Bohr model. So the electrons have fixed energies, and these are like rungs on a ladder. So if you have somebody climbing a ladder, they can only step on the ladder rungs. Okay, you won't find them in between the rungs. And notice that this ladder is a little bit wacky, and that is because it is representing the electrons' orbits. So the first 3 orbits, you can see they're spaced more far apart, but then when you get to the 4th, 5th, 6th, 7th orbits or energy levels, you have they're a little bit closer. That's because they're closer in energy. So let's look at energy and light and quantum theory. So electrons are very mobile. They can move from atom to atom, and when they do that, we can have bonding. But what we want to focus on here is looking at the electrons in just one atom. When these electrons in the atom are exposed to energy, they get excited, they absorb that energy, and they will jump to a higher energy level. So oftentimes it's called a quantum leap or a quantum jump because it takes in a certain amount of energy and that in turn translates it to going to an excited state. So it just means that it jumps further away from the nucleus. So in this picture, you can see that we have some sort of energy coming in, and we have our electron moving from the ground state where it typically is, and it will go to this excited state. Now, it does not stay in that excited state for a long time. Immediately, it will fall back to its ground state, and it can do it in steps, going on each of those energy levels, or it can do it all at once. And when this happens, when it goes back, it will release that energy that it had absorbed in the form of light, and we can see that. And here, this picture in black, you can see um, another picture of this. So again, here's the ground state. It absorbs some sort of light or heat that comes into the atom. The electron will jump up and to that excited state, and it won't stay there forever. It will immediately jump back down. It can jump back down by energy level or all at once. And when it does, it releases that energy in the form of light. So just to recap, electrons can't go in between energy levels. You'll only find them on the energy level. And when they absorb the energy, so if I had an electron right here, it can jump up several energy levels, so even all the way up to here. And again, it does not stay in that excited state for a long time. Instead, it can jump down orbit by orbit. And when it does that, it can release that energy in the form of light. So if it's a step by step, because it's releasing less energy as it goes, the amount of energy in that light will be less. However, if it jumps all at once, so it does a big jump, you will see that energy in the form of a color of light that has more energy. And over here in this little box, it just shows those energy levels. So our first energy level, our second energy level, third energy level, fourth energy level. So you can see as you go out to away from the nucleus, the energy levels get a little bit closer together. So again, your energy level 1 is, so we can say energy level 1 or N is very, very close to the nucleus, where energy level 4 here would be further away. So in class, we are going to do flame tests. So if you're looking at this at home and you miss this activity, you will want to go on YouTube and search flame tests or chemistry flame tests and just look and see what we're talking about. Basically, we're using heat to excite electrons, and in return, we are able to see when the electrons drop from their excited state to the ground state, they will emit that energy in the form of light that we can see. And every element has its own flame test signature. So we might see reds and greens and blues and purples and oranges, and those all are identified depending on what your element is. So we can plot the energy given off by an atom with its electrons jumping back from its excited state to the ground state using waves. So this is where there's a lot of physics and chemistry. So if you've studied a physics class, you might have already studied waves. So frequency in chemistry is represented by this little letter. It's a Greek letter called nu. It looks like a little cursive V. So frequency is measuring how many waves go by in a second. So if I look at this wave right here, and here's my eyeball, okay, and I count how many waves are coming towards my eyeball, I can count from wavelength to wavelength, from crest to crest. That is represented as one wavelength. And so frequency is measured in how many wavelengths per second. And so it has a unit of 1 over S, or S to the negative 1, or sometimes it's given the unit hertz, but all of those are equal to each other. So it means 1 wave per second, or how many waves per second. Wavelength, as I already pointed out, it is from crest to crest, and it is represented by the Greek letter lambda. So it looks kind of like a funny looking H that is maybe going backwards. And this is measured in meters or nanometers. And we often will use nanometers in our calculations. So make sure that you remember that 1 nanometer is equal to 10 to the negative 9th meters. The speed that all this light travels is the speed of light, and that is represented as the letter C. So C is the speed of light, just like in Einstein's famous equation, E equals mc squared. That c is the speed of light. So, and its units are 3 times 10 to the 8th meters per second. Now in this diagram we have amplitude, and it's really not that important in chemistry, but what amplitude tells you is the brightness of the light. So if it was really a bright light that was coming out of the atom, it would have a very large amplitude. If it was a very weak light, so not very bright, it would have a shorter amplitude. So here's the equation that relates the speed of light to the wavelength and to frequency. And we are going to have problems where you will have to solve for the unknown. So you will be given 2 out of the 3 letters in the formula, and then you'll have to solve for the unknown. And so you can manipulate this wavelength and frequency formula to solve for frequency. So if I wanted to get frequency all by itself, I would divide each side by the wavelength. So frequency would cancel, and I would get wavelength is equal to the speed of light over the wavelength. And you could actually flip this around, so it looks like this. All right, so there is one formula that I could get from my speed of light formula. You also could solve for the wavelength. So maybe the wavelength is unknown, but you know the frequency. So I'm going to divide each side by the frequency. So you would cancel that out, and I would have wavelength is equal to the speed of light divided by the frequency, or I could flip that around. So this is one equation, one formula that I can manipulate. So I can solve for the frequency, or I can solve for the wavelength, depending on what is needed. So let's go ahead and try a problem here. So an electromagnetic wave has a frequency of 5 times 10 to the 4th, 1 over s. Find the wavelength. So I find in these problems it's helpful to identify what each of the numbers are. So frequency is given the symbol of that nu, that funny looking V. And it says find the wavelength. So I do not know the wavelength. So what equation do you know? And we only know one equation that has both of these things in it, and it is the speed of light equals wavelength times the frequency. And so we need to find the wavelength. So I'm going to use that wavelength equation. So I have the speed of light over the frequency. If you don't like rearranging this speed of light equation, you can just plug the values right into that formula. Just remember to follow all your algebra rules. So the speed of light is 3 times 10 to the 8th meters per second. And my frequency given to me is 5 times 10 to the 4th. And that s to negative 1 is 1 over s. So you can see that your seconds is going to cancel, and my unit is going to be in meters. So we take 3 to the 8th divided by 5 times 10 to the 4th. Make sure you use your exponent button on your calculator. So don't use the caret button. So you would type in 3, that exponent button. Most people have an EE or an EXP button. And then you'll do the letter 8. And then you'll press divided by sign. And then 5, EE, and then the 4. So don't use your caret button, make sure you use the exponent button. So the answer that I get when I press enter, I get 6,000 meters. So this is the wavelength of this wavelength of light. All right, let's look at electromagnetic spectrums. I do have a video right here that explains the different types of waves that are in the electromagnetic spectrum. They range from radio to gamma rays and everything in between. So we have microwaves, infrared, visible light rays, ultraviolet, X-rays. There's also a chart like this in your packet that you can see. When you look at the visible light, what we truly can see, we can only see a very narrow band. So just the only thing we can see is anything that fits in this range here. So in this picture kind of expands it. So I can expand it to the colors of the rainbow. Roy G. Biv. So maybe you've learned this before in elementary school. So we have red, orange, yellow, green, blue, indigo, and violet. So you can see that the electromagnetic spectrum in this picture, it is set up according to energy. I have a high amount of energy over here, and I have a low amount of energy over here. And that kind of makes sense. So gamma rays can kill me. They have a high amount of energy, where radio waves won't kill me. Thank goodness. Okay. Um, so we can look at also frequency here. So frequency is listed right here. And so notice over here that I have a high frequency over here, and on the other side I have a low frequency. And let's look at wavelength. We can't neglect that. So in wavelength, I end up having very short wavelengths here, and over here I have very long wavelengths. So let's look at and define the relationship. So a direct relationship. So if I have a high amount of energy, what else is also high? And you can see that I would also have a high frequency. So those are a direct relationship. So as my energy goes up, my frequency will go up, and vice versa. If my frequency goes down, my energy will go down. What is an inverse relationship? Well, I can see that if I have a short or a small wavelength, that I have a high frequency. And also we can look at energy. If I have a short wavelength, I also have a high energy. So this is an inverse relationship. So direct means that if one goes up, the other one will go up too, or if it goes down, the other one will go down too. And then inverse means if one goes up, the other one will go down. And obviously the opposite are in play there. So if I had a very long wavelength, I would have a very small frequency. If I had a very long wavelength, I would have a very small amount of energy. So in your packet, you want to identify high energy, low energy, short wavelength, long wavelength, low frequency, and high frequency according to the electromagnetic spectrum. Let's look a little bit more detail with the visible light. So when we look at visible light, we see that red has a very long wavelength, and the indigo and the blue has a very short wavelength. And so that gives you a little clue on the energy. I have a smaller energy with the red, and I have a larger energy with your indigo and your blue and your violet. And then you have the ones in between. Okay, so red light has a long wavelength and less energy. Blue light has a short wavelength and more energy. And just for fun, so looking at the epic battle between Obi-Wan Kenobi and Darth Vader, we see Vader has a red lightsaber and Obi-Wan Kenobi has a blue or purplish lightsaber. So who truly should have won? And it should have been Obi-Wan because his lightsaber was more powerful. It had more energy. Just for fun. So let's look at a little bit more and dive in deeper with Max Planck in 1900. He was commissioned by the German government to build a better light bulb. Back then, the light bulbs gave out a lot of heat, and the German government wanted to have a light bulb that the energy wouldn't be wasted so much in heat. Instead, that the energy could be poured out in light. So to transfer that electricity more to light and less to heat. And so Max Planck studied this problem. He studied what's called black body radiation. And this is a picture right here. This is black body radiation. So when you have a piece of metal and you heat it up, it starts glowing. And so this is what he studied. And he said that light waves carry energy in little packets, and each packet could be different colors. The packet of energy, he called it quantum. So that's where the word comes from. Max Planck, he was one that came up with that term. And so basically this is a photon. So he said that when you have this piece of metal that heats up, the energy is released as a photon, a little packet of energy. And when Planck did all his calculations, his numbers were off by just a little bit. And he couldn't figure out why. And instead of fudging his numbers and saying, oh, I just probably made a mistake, he just turned it over to the scientific community and he said, something's going wrong with my calculations. I can't figure it out. All my amounts are off by just a little bit. Maybe some other scientists can figure it out. And the scientific community went and looked at Max Planck's calculations, and they said, no, you discovered something new and unique. Um, this is a new part of science. And so we get Planck's equation, which is right here. Energy equals Planck's constant, so it's a little h there, times the frequency. And there is the value for Planck's constant. So notice that this equation also has frequency, just like that last equation that we did. And so we can use both of these equations to sum up the energy given off by an atom when its electrons go from excited state to their ground state. Another scientist that also studied this little packets of energy was Einstein, and he actually got the Nobel Prize for it. And this is called the photoelectric effect. And Einstein said that when we have certain wavelengths of light hit metals, electrons can be given off. So it has to be at a certain frequency. So maybe we have some red light come in, and then maybe nothing happens because of that. But if we have enough energy, so maybe some violet light come in, then that will cause these electrons to be emitted from the metal. So again, we have two equations here. So we have our energy equation and we have our speed of light equation. So all these equations will be given to you on the test. They are in your homework packet. So you can open up your homework packet and you can do that first page of problems using these. As you go through and do each of the problems, make sure you identify if a number is energy, if it's frequency, or if it's wavelength. And then remember you have two constants, and that means they always stay the same. So we have our Planck's constant, which looks like an H, and we have our speed of light here, which is a C. Make sure you use your exponent button because your calculations will get really, really wacky unless you do. So let's do this problem together. A photon of light has a frequency of, so here's my frequency, and then it says find the energy released. So I need to figure out what the energy is. So what equation has frequency and energy? Well, it's that first one. So energy equals Planck's constant times the frequency. So let's plug in what we know. So 6.626 times 10 to the negative 34. And it's joules times seconds. It can also be represented as joules divided by hertz. Because remember, 1 hertz is equal to 1 over s, 1 over second. And then we have our frequency that they give us. So 5.04 times 10 to the 14th. And it's 1 over s. Notice my seconds will cancel, and I'll be left with my unit in joules. So this would be 1 photon and how much energy in that 1 photon. So this one little packet of light given off by the electron. So I'm typing this into my calculator using my exponent button. So 5.04 exponent 14. And we get 3.3395. Boy, that's a lot of numbers there. To the negative 19th. Let's go ahead and look at significant digits. So the number that we start with are sig figs. It looks like there's 3. So remember that in scientific notation, you only write what is significant. So I should cut this off at 3. So rounding this to the proper sig figs, I would have 3.34, and don't forget to tack on that times 10 to the negative 19. So this is a very, very small amount of energy because it's only 1 photon. It's only one little packet of light that was released by the atom when the electron went back to its ground state from its excited state. Let's do another problem. A photon of light has a wavelength of 850 nanometers. Find the frequency and energy released. Now, there's a problem in that the speed of light is represented as 3 times 10 to the 8th meters per second. So if I'm going to use the speed of light, I need to be in meters. Notice this is in nanometers. So I need to know how to convert from nanometers to meters. And really, all you need to do this, there's kind of a long way to do this and a short way. The short way is just to scribble out the nanometers and tack on times 10 to the negative ninth meters. Okay, so it's not written in scientific notation, but we're just scribbling out the nanometers and putting times 10 to the negative ninth, because that's the equivalency of nanometers to meters. So knowing that, we need to look at this problem. So we have a wavelength. So here's my wavelength. And that says find the frequency and then find the energy. So we have to find both of those things. So first of all, which equation has wavelength in it? You're right, it's that speed of light equation, that one right there. So we're going to use this one first. Now I'm going to solve for frequency because that's what they want me to find. So again, manipulating my equation, I'll have speed of light over wavelength. So speed of light, 3 times 10 to the 8th meters per second. And my wavelength needs to be in meters, so I take that 850 and I tack on times 10 to the negative ninth, and it's in meters. My meters cancel, and I'm left with my unit 1 over s. So let's go ahead and plug that in. So we have 3 exponent button, 8 divided by 550, exponent button, negative 9. And I get, oh, it didn't write in scientific notation for me, darn it. So 3.529, I'm going to carry an extra sig fig, times 10 to the, let's see, 3, 6, 9, 12, 13, 14. To the 14th. So that's a very, very large number. That's the frequency. So how many wavelengths are going by per second? So that's a lot. Okay. Let's look at our next equation. So we have our energy equation, Planck's constant times the frequency. So Planck's constant 6.63 times 10 to the negative 34th joules second, and multiply by that frequency that I have, and 1 over s. So you can see that my seconds is going to cancel, and I'm going to be left with joules. And let's go ahead and put that into our equation. And I get for my joules 2.34 times 10 to the negative 19th joules. So this is my energy. So I found my frequency first, and then with that I was able to plug it into the next equation to find my energy. So it's just one photon has this little tiny bit amount of light. When you look at a flame test, you see the dominant color of those photons that are emitted when an electron falls back to its ground state. When we look at white light, we see that it contains all the colors of the rainbow. So red, orange, yellow, green, blue, indigo, violet. If you take and you excite the electrons in a gas and then put it through a prism, you see what's called an emission spectrum. So what happens is these wavelengths, they are absorbed by the electron, and then they are emitted in the form of this light that we can see when that electron drops back down to a lower energy level. When you look at a flame test, you're really just seeing the dominant color, but there actually are more colors involved in that dominant color. So for example, right here with hydrogen, the dominant color is more like a blue-green, but there's also violet and blue-violet and red there too. And only with the prism are you able to see that spread out. So here are some elemental emission spectrums. So we see hydrogen there at the top. So this one is even more detail. So you can see more lines in that violet region. When you look at sodium, the flame test is really yellow. And when you put it in a prism, you can see those very strong yellow wavelengths. And there's helium there and neon, and also mercury down there at the bottom. So every single element has its own spectral signature. So it's kind of like a fingerprint for the elements. So when they were first identifying and verifying different elements that were discovered, they would use a flame test. But there's only some of the elements had similar flame tests, so then they needed something else to identify an unknown element. And so then they turned to these emission spectrum. So you can look at the light that's emitted through the prism and you can identify what an element is from its emission spectra. You also can get a combination of spectra. So right here, there at the bottom, we have a combination of hydrogen, carbon, and oxygen. So all together, you would see all those various lines. So you would need to be able to tease out and figure out what elements are there. And so looking at hydrogen, carbon, and oxygen, you see that all of those are contained in the mixture. So down here at the bottom, we have an unknown mixture here. Can you figure out what elements are there? Can you figure out what elements are not there? So stop the video and see if you can figure it out. Okay, so you want to line them all up. And if there is a band of light or a color that is not in the mixture, then you know that you do not have that element. So looking here, I see that there is no barium. And that's because it has all of the lines except for this one. So this one is not found in the mixture. So as a result, you would say there is no barium in that mixture. What would be there? So if you look at the very, very top one, you would say that there is calcium. So looking, you would have every single line of calcium would be represented in that mixture. So you would say, yes, you would have calcium. And there are other ones in there also, but that's just an example of one that's not there and one that is there. So when we look at the Bohr model, so he said electrons are in definite energy levels, and so they are mobile. They can jump up to excited states or excited energy levels, but they don't stay there forever. They'll drop back down to lower energy levels. And then when they drop back down, they emit energy in the form of light. So this is how we know what elements are out in the galaxy. So we can look at a cloud of gas in space, and we can look at the light through a prism, and we can come up with that mixture light signature there, and we can tease it apart and figure out what elements are there. So that's how we can figure out what is on a planet or a star without actually having to visit.